Good morning. Good morning. Such wonderful learning to happen today. Such wonderful learning. So, the first priority that I have is to make sure that we're comfortable and understand the differences between our periodic families. So, we'll go over our homework first. If you could turn to page 25 in your unit packet, we will answer additional questions to see what needs clarification. Then we'll get into periodic trends. And so excited for that. And we'll do some work in our teams and just wonderful. So I have 3 goals. 1, to make sure that we understand differences between our periodic families. What do we have to know, in essence? Because that will be quizzed on Monday. Yeah. Then, and look at some sample questions. Then work in our teams to start on the first periodic trend. And we'll take our time a bit with the first periodic trend. I understand you're probably thinking, periodic trend, what is that? Don't worry, we'll talk about it. As long as we really, really take our time with the first periodic trend, all the others fall right into place. So by the end, periodic table families, what do we need to know? Do we understand everything? Then, what are the trends of atomic size, ionization energy, electron affinity? That's what we'll be working on today. All right, so first, can I ask you to go ahead and check your answers with mine just for the top here, and then we'll go through the others. So I'll address. Yes, yeah. So we go through this, or before we. Yes. Okay. Yep. It's so good to see you. Feeling okay? Yeah. Better, but not 100% yet? Yeah. Okay. So glad to see you today. If you have any feeling of any, you just let me know. Interrupt. So Ava and Ali and Nathan, yesterday, we got our quizzes back. So I have those up front. I'll get them back in your hands in a bit. We looked at that first, then we completed the demonstrations to see the reactivity of sodium, or lithium versus sodium versus potassium. And then I'll put something else in your hands in a moment. We went through a bit of a streamlined approach to our different periodic families. And then we had this for homework. So that's what was accomplished yesterday. Questions here? All right. So 2 other elements with similar chemical properties to iodine, we would definitely predict any, right? Any of the halogens. So I just did bromine, chlorine. Those are the closest. So if given the choice, I would go with those. Just acetine, you could definitely say that, or fluorine, definitely say that. Any of those, yeah? Okay, then what should we not store next to each other? Well, how about the most reactive metals and the most reactive non-metals? Imagine if a shelf would fail. We know that things like that happen in cabinets. So the way that we store chemicals, and chemists, pharmaceutical companies, is so that if there would be an accident and chemicals, bottles broke and so on, what would mix will not react with each other. We keep the acids all separate. Some acids can't even be stored together. We keep nitrates separate from. So anyway. All right, next. What if you needed to satisfy the criteria here? The best choice, germanium. Yes. Thank you so much for asking for clarification. I appreciate that greatly. Okay. So as soon as it says electronic device, my brain thinks, oh, so like probably a conductor is needed? Maybe. So I'm thinking like, oh, well, maybe a metal. We know those are excellent conductors of electricity. Non-metals are not. All right. They need an element that has chemical behavior similar to Si and lead. So I'm going to go to the periodic table because I know near silicon and near lead, those will have similar properties. That's why we place things where we do. So I kind of look there. All right. The element must have an atomic mass greater than that of sulfur. So let me just show you where my. So it's saying between this and this. And I would definitely think, okay, we're going to want to be in this general area. I mean, am I talking about all the rest? Probably not, because it says similar. All right. It must have an atomic mass greater than sulfur. Okay, sulfur's 32. So that takes out like these, yeah. But less than cadmium. So here's cadmium. It has to be over 32, but under 112. So that takes out these. Okay. And we're just asked to just choose one. So I'm going to choose one that's near these. I have my mass constraints. So I'm going to choose germanium because that's in the same family. We definitely know neighbors are going to be similar in their behavior and in their physical and chemical properties. So now I would accept if this was on a quiz, you could see two metalloid. So that's like something else in his favor, but yet, so we could choose this. We could choose this. We could, but would we choose a noble gas? We could expand out from there, but if possible, in the same family would be the best. Okay. Any other concerns? Okay. Incredible students. Could we please? Oh, I'm sorry. I get a little post-it with all the order that I wanted to go in. Don't you know? Phooey. It's here somewhere. All right. Could I ask us, amazing students, to please turn to the very last page of your packet? Okay. Can I ask you to match 31 through 41? And you're matching it to the elements. Or if you vote, online or a picture of someone else. That we did not do anything after the cover here. We just used them as green line or boxes and sure what I wrote or get a picture of someone else's to fill that in. Okay, you're very, very welcome. I love this matching because it's not giving us alkali metal, transition metal. It's giving us an example. That is, what we're doing, striving for. Okay, so 31B, 32D, 33E, 34C, even though now we're categorizing. But anyway, 35 is A, 36 is E, 37 D, 38 A, 39 D, 40 C, 41 B. I know I just said they don't give you alkaline, but I mean the letter choices. Questions? Yes, ma'am. Yeah. Yes, yes. Now, not always, but now, yes. For now, we are just, because we're just getting into this, for now, we're going to say that nonmetals, they usually form anions. They're going to form anions, but we'll see some exceptions to come. But metals can only and will only form cations, period, done. Did that address what you need? Yes, Eddie. No. The reason is this. Every member of column 1 always forms +1. That's it. That is it. That is it. Every member of column 2, +2. That's it. But our transition metals, they are going to be positive because they're metals. I have to tell you now what the numerical value is, but we'll see next chapter that you can determine it from a given formula. You'll be able to find it out, except for silver, zinc, and cadmium. So copper, it forms multiple cation charges. It's just transition metals. Now, that property also carries a little over into the B block, but theoretically and truly, transition metals are only D block. Did that address what you need? Jeremy? Yeah. But how do you know that copper is +2? Right. But not all transition metals form a +2. We'll find the range of cation charges from 1 to 7, but that doesn't mean they form +1, +2, +3, +4. We don't have to know this. We do not have to know this. Don't have to know this. Copper, I just was using this with the second year students. Copper is +1 and +2, but we don't have to know that at all. But look, chromium, the most common ion is +3 and +1. So we just can't assume. But that's what I was going to say. How do you know that copper is +2? Because it often is found as +2. So I just thought you just knew that. But we don't just know that. We just know positive, but there's a range. I just want to go back to that, right? It's going to be a cation. These are the most common charges they could be, but it doesn't mean they are all these charges. Is that okay? If I would ask you, what is the charge that iron forms as an ion? You would say, Miss Garrett, I can't tell you specifically. I can only tell you because it's a metal, it'll form a cation. What is the charge of silver? Oh, well, that is a transition metal, but it always forms the same charge. We need to know silver is +1. What is the charge of tungsten? We don't know the actual value. We know it's going to be positive because it's a metal. Okay. Jeremy, is that still like too gray? Does it feel a little more black and white? Clear? Okay. Yes. Yes. Always, 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 always. Yes. No. Silver, you mean? Oh. No. Silver is the only one in the D block that we know always is +1. Always. That's the only one that we always know is +1. The only other two transition metals that always form a +2 are these two. These are going to be positive, but we need more information to say the magnitude of the charge. Did that address what you need? Okay. So can I ask us now, same page. Oh, any other concerns? So same page, could I ask you to please answer 27, 28, and 30? Jack, do you mind sharing? What did you choose for 27?
Said B, their electron and
Fantastic. Jake, what about 28, sir? Excellent. And let's see. Talia, what about 30? Ah, excellent. Questions? Yes. Okay. I'm sorry. You're choosing a property that does not belong with metals. They do. Which of the following is not a property of a metal? You're finding the one that doesn't apply to metals. Metals are malleable. Metals do conduct electricity. Metals react with acid. I'm so sorry. I know. That's why I write it too. Just know that. That's why I write it there as well, because I know sometimes those letters sound the same. Okay. Can we just do a couple more? How about 18 through 23? On 35. I'm so sorry. The page before. 18 through 23. I apologize. Page 35. Okay. Cameron, do you mind sharing the first 3 choices that you made? Excellent. EBA. Excellent. Jake W. The next 3, please. Excellent. Questions? I saw some of you moving on from there. So 24 would be D, 25 would be B, and 26 would be E. These harken back to like what our first quiz involved. So that's why I was focusing on these. Okay, that is the content stuff that we need to know. What I would suggest, sometimes in preparation for a test, we'll just look over our notes. And that can mislead us. That can mislead us because we're really not engaging with it. We're just kind of glazing over. Sometimes it's fine to just look at your notes. But to actually like interact, I can help, but just suggest, not required, just a suggestion. Here are our different families, right? We got this yesterday, but we didn't do the front. So this could be study practice, learning practice. So the alkali metals, can you fill in everything? Alkaline earth, and so on and so on. So that is a good, better way actually write than just look over. Just a suggestion. Okay, but if you were easy peasy, able to answer those with no sweat, we want to make sure that we're good on those. Okay, questions for me? It'll have the same amount of, be the same quantity of questions like our first quiz. All right, so we're going to transition to then periodic trends. So I'm going to ask you first to do something in your team. I'm going to give each team one. I'll just give it to the middle seat. That doesn't mean the middle seat has to be right or down. And if you each like a copy, you definitely can. How about you guys want to be a 5 or 0? All right. So what? Sorry about that. Yeah. Okay. So, do we need another? That's okay because we usually pass the 5. I totally know. Hey, are you okay?
So it like this just this morning. Like I'm back and I was like, I'm back better than ever. And then this morning I put on the morning announcements and just kind of talking that.
But now you're in chemistry.
I know, so much better now.
Yeah, let's just right back. All right. a trend, a trend. We now are going to encounter concepts, new things that based upon where an element is on the periodic table, we can answer like how large in general is arsenic compared to copper? What about copper compared to gold? So the most important trend for us to understand is as we move from left to right across the periodic table, through a period, do our atoms get larger? Do they get smaller? Or the size stays the same? How about as we proceed down a group? Do atoms get bigger? Do they get smaller? Do they not change in shape? Size is the key to all the other trends, because then we'll ask, what about ionization energy? Does it increase, decrease, stay the same? Increase, decrease, stay the same. That's what we mean by trends. Okay, so in your team, what you're doing is predicting. Educated guess. You guys are brilliant, brilliant. So what do you think as a team, when you move down a group, does the size of the atom increase, decrease, remain constant? And then why do you think? And then across a period. Then on the back, easy peasy. I hope this does not insult your intelligence. First, I'm so sorry, typo error. This is TL, not TH. So we're just boron to neon and then B to TL. All we're doing is filling in, okay, how many protons do these guys have? And then what is the highest energy level that has electrons for these and these? Okay, take it away. Understand why you made the predictions you did. 1,000,000%. I think that just is kind of logical, yeah? That as, we go down a group, top to bottom, getting bigger, across a period, getting bigger. Please, please, please take a look. So can you make sure you have this side? Do we understand what holds electrons in an atom? What holds electrons in an atom? Can everybody think of the answer? What holds the electrons in the atom? Just like I could ask you, what keeps the Earth in the solar system? No, not the same reason. But what actually keeps the electrons in the atom? Go ahead, Preston. Okay. But you know what? Well, okay, they're going to be in orbitals, but what is different between why can't the electrons just kind of pair up out here, or if that's in the nucleus? So yeah, but why? So we'll add to yours. You're right, that's where we're gonna find them. Yeah, but why do they even get created? Go ahead, Jake. No, what holds the electron there? And so why doesn't an electron just go on its merry way? Gravity? Any two samples of matter exert a gravitational force on each other. Any two. But it's the greater the difference in mass. Yeah. So right now, you are exerting gravitational force on Bailey. You're exerting gravitational force on Jake W, on Eddie, on Jake. But you guys are comparable masses. So, but the Earth, so much more. Okay. Well, oh, electron is so pathetic in its mass. But there's a greater reason that is stronger that keeps the electron in the atom. Jeremy, take it away. What about the proton? Opposite charges attract. We know this. That's one of our strongest, well, besides the nuclear force. So in nuclear reactions, nuclear power, atomic explosions, besides that, electrostatic attraction, opposite charges attracting, that's our strongest force. Positive and negative. So now we know the electron is going to get consumed by the nucleus unless it's moving. But what keeps it in the atom is the electrostatic attraction, negative to positive. Or is that okay? Preston, is that okay? Okay. What is going on as we go from left to right with our nuclei? Obviously, we're adding more protons. Our number of protons, you know what? I think we do. I do want to give us, you don't have to fill this in if it's not yet. I tell you what, could I actually, I will collect the one that you've written on. Okay. I will collect the one you've written on. So just for sake of writing. So the ones I'm handing out now are your, there's methods to the madness. No, same. Again, there's methods to madness. These are for you to keep. I'm gonna collect the T one. You'll it all makes sense. Okay. We, as chemists, give the number of protons in the nucleus a special name. We call that the nuclear strength, the strength of the nucleus. The more protons, the more positive, the stronger the nucleus. If we want to think about magnets, you can have different strengths of magnets. Yeah. So I keep magnets to pull things up. And there's some magnets that are just really decorative. I could not, I'm sure, use this to hold up papers. It's not strong enough. Now, it'll hold itself, but not, it's not strong enough to transmit through the papers. But this magnet, so we know there can be different strengths of magnets. Well, it's along the same line. So we can imagine that the more protons, the greater the strength of the magnet. Across a period, nuclear strength increases, more protons. But what about, Ryan, as we proceed down a group? What happens with nuclear strength? Yeah. In fact, here we're just adding one proton, one proton, one proton. Here, 8 more, and so on and so on and so on. But it's not just how positive is the nucleus. James, you choose. Do we want to take a 4-minute now or finish this 4 minutes after? I guess the music decided for us. All right. 4 minutes now. Q equals MC delta T. So when we had that open triangle or shaded in triangle T. Anybody? Bailey. Yes. Absolutely. That triangle we could say means like a translation. If I had to write out instead of putting that triangle, it would be change in nuclear strength. So as we are moving down a group or across a period, how is nuclear strength changing? Well, in this direction, increasing, in this direction, increasing. Yeah? But we have something else to look at. So, what is that other thing? Because it's not just about the nucleus. You're right. You're right. You're right. That's nuclear strength, right? The number of protons. The energy levels of the electrons. Yes, 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 yes. Change in energy level. Okay, so look. As you go across the period, how is energy level changing? Stays the same. It's not. As you go downward. And so if we could imagine, like picture in your head a nucleus, and then what does it mean when this is 2 versus 3 versus 4, and so on and so on. So nuclear strength increasing, nuclear strength increasing, both directions. But here, electrons added to the same energy level, here, consecutively far energy levels. Back to the one that you were writing on in your teams. One of the directions is contrary to common sense. One of the directions is contrary to common sense. In one direction, atomic size increases. In another direction, it decreases. So here is take 2. As a team, in what direction across a period or down a column are you decreasing and why? Take 2 or 3 minutes. Talk. We're always going down a column and across a period. Because if you're increasing this way, we're decreasing that way. That's not what's, you see, we're always going to go left to right. Yeah. Down a column, atomic size increase. Or, oh my goodness! No one stop me. That's wrong. Arrow should be down. Sorry. Okay, atomic size decreases. As we go down a column, atomic size increases. Okay. Can we go to our unit packet, please? And page 14. Okay, I am going to just sketch a periodic table, just sketch. Sorry about that one. Okay, so we know we have 7 periods. I'm just going to write 5 and then 18 columns. Okay, well, nucleus is getting more and more and more and more powerful down a column. However, our energy levels, first energy level, yeah, second energy level, third energy level, 4 energy level, 5, whoa, 6. Yeah. Versus across the period, page 14, versus across the period, second energy level, and our nucleus is getting more and more powerful. So we can see, oh, we're definitely getting bigger as we go down. Try to make that. But as we go left to right, we decrease in size. Ryan, if you wouldn't mind helping me. Okay, so across a period, the size go up, size goes down. Yep. Down a column. Yeah. Okay. Change in nuclear strength, Ryan. As we go from left to right, does it increase or decrease? Say again? Absolutely. Change in energy level, Ryan? Yeah, there's no change, stays the same. All right. Down a group, Eddie, how is nuclear strength changing down a group? Increase, decrease, stay the same. But what's going on with our change in energy level? Yeah. Okay, so now you guys again. This is like the what. What's going on? But we're still trying to get like the why. So back to the one that as a team you were writing on. Do you have room on the back Okay, as a team, you know the what. And this is what as well. Yeah. We get larger, we get smaller. That's what's going on. But how does that explain why we get larger, we get smaller? So could I ask us now, talk in your team, why the size increase down a column versus why size decreases across a period? Why don't they both increase as you predicted first? Go. Talk to each other, and then ultimately write down what your thoughts are. Yeah. It does. Okay. Potassium hypertrophy. We start in the 4S. Then, yeah, we go actually closer. But then we go back to 4. We're not going further. D and S. D and S, if it's near energy level. So like the 4S and the 3D, they're really close to energy. The 5S and the 4D, really close to energy. So it's kind of like we're adding to the thing.
Eventually it just goes back to energy level at.
Yeah. And I'll tell you what, P is a little higher in energy, but that's just the way, you know, okay? Does that address what you need? Before we talk about very interesting. Very interesting. Yeah. Anybody need any guidance?
Dude, like, I just don't understand, like, why?
Okay. It totally is confusing. It totally is confusing. I don't know because I haven't been there for a while. The Science Museum in Pittsburgh. So the top level is like the water table that you can. Is it still? I haven't been there a while. Oh, did they move? But do they still have? It was like a big. It was. Oh golly, almost as big as this room. That it had like a big table that was the size of like toddlers. And then they had like little waterfalls and then little paths that the water would go. And they had all these things like little boats and everything. And you put on like an apron so you wouldn't get all watered and drenched, even though my kids would always get. That's what do they still have that? Oh, right. Well, then I remember because especially my Noah, he is a builder. He's just made that. He just loves to build. And on that top floor that they used to have the water table, when you first got off, there was this huge, like, it looked like a big stick up thing that they had a bunch of pipes and stuff, and it was magnetic. And you could just stick the pipes, and then you had ping pong balls, and you could make the ping pong balls go all the way through. Is that so? Okay. Can we imagine? So big, like this kind of wall thing, a separator that was all magnetic, and then you could Just stick things. Okay. Well, they had a sign on it. Do not bring any credit cards close to the magnet. Now that's before check. So just the magnetic strip. If you bring a magnetic strip to a really strong magnet, it'll demagnetize and then ineffective debit card or credit card. Well, being a mom, purses just get in the way when they were little. And so I would always in my pockets have my credit card or debit or whatever. So I knew, oh, I can't walk near that big magnet. I need to walk. So Noah, you go ahead and play, but I'm just going to watch from over here. Or could I somehow, I don't know, protect that? So even though it's a really, really powerful magnet, with distance, I really don't feel the magnetic pull. Is that okay? Ava, does that like make sense? So you could have a really, really strong magnet, but if you're really far away, who cares? You're not going to feel that pull. Is that okay? Just does that make sense? Then we'll say why the atom. Why am I even talking about this?
Yeah.
Okay. As we proceed down a group, we are adding more and more and more protons. So, like if we go from lithium to sodium to potassium, and so on, more and more protons. So it's like a stronger, stronger, stronger magnet. But also, Ava, as we proceed downward, we're adding the electrons to further and further and further away energy levels. So even though our nucleus is getting more powerful, we're adding the electrons further and further and further. So our atoms get bigger. Is that okay? Bless you. But then why across a period? So as we go across a period, our nuclear strength is increasing. And here it gets to show itself. Because you're not adding the electrons any further. So it's becoming stronger in its pull, stronger in its pull, stronger in its pull, stronger in its pull. The electrons are being added the same distance so that more powerful nucleus will pull those electrons inward. Jeremy and Ryan, did you write something? Would you mind at all reading aloud? Yes.
As we go across.
I put your answer on the document. With that, is that okay? Do I have your permission to do that? Okay. We know that we get better and better and better with explanations, and explanations are hard. Okay. Size increases across the period. Wonderful, wonderful, wonderful. All right. They are in the same energy level. What are they? Yeah. Electrons, and we're talking about across, they're being added. Yeah. Electrons added to the same energy level. Okay, I'll take but the atomic strength is going up, more protons. So the electrons get closer. You see, we need something there. Well, why are they getting closer? Because there's more protons? But why? What are more protons going to do with the electrons? Why? So it equals a stronger pull of nucleus for electrons. So thank you so much for reading. Thank you so much. That just puts it over the top. It was a good answer to start with, but adding those little details. Whenever we can be more specific, we always want to be. So instead of they, it, what are you talking about? Okay. So size increases down a column because the valence electrons get further away. We need more. What do we know about each move to a new period? As or when a new period, electrons added to further away energy levels. And that's fine. That's enough. Okay. Ava, did that give a little bit more? Okay. Let's put yourself out there. Okay. Did we get to, as a team, write your answer? Okay, how about this? Could I ask us in our unit packet, please? Back to that page 25 that we did 1, 2, and 3 for homework. Okay, amazing students. So could I ask us to do number 4? Again, page 25. What you're doing is between the 2 that you're given in each letter, which is larger? So aluminum boron, which is larger. Sodium, and which is larger. So go ahead. Bless you. All right. A, aluminum. B, sulfur. C, bromine. D, sodium. E, oxygen. F, calcium. So, just based upon placement, can we choose larger or smaller? If we were given a collection together, so what if we were given aluminum, phosphorus, chlorine, and sodium, multiple members, could we rank them in increasing size or decreasing size? But most importantly, can we explain why? All right. Can we go back? Can we get 1 or 2 more things? And then we'll wrap up. So, page 15, please. All right. We're not going to do ionic radius. That will be left if you choose to study more chemistry in second year AP chemistry. So ignore that. Electronegativity, we'll actually leave that for last. So ionization energy. Can we just get what it is and electron affinity, what it is? Okay, ionization energy, the energy required to remove an electron from an atom or ion. The energy required to remove an electron from an atom or ion. You have my total permission to represent ionization energy with a capital I and a capital E. Ionization energy. So, what are we doing? Well, if we have element X, if we invest enough energy, we kick out an electron. Okay, Allie, if we remove an electron from X, what changes about it? Wonderful. So this is cation formation. Yeah? We're forming cations. If we are removing the first from neutral atom, we call that ionization energy 1. But we can keep removing electrons. So if we remove a second electron, after we've removed the first, we call that ionization energy 2. And then we would form a +2 cation. Okay, electron affinity. Energy released when electron added to an atom or ion. So we're adding an electron, not energy. We're adding an electron that releases energy. And we're forming an anion. The trends all based on size. All based on size. Okie dokie. Page 28, please. Okay. Could I ask us, we will go over this before our quiz on Monday. Could I just ask you, page 28, might take you 4 minutes maybe. Could I just ask you to answer 1 through 5? Oh gosh, well, we'll go over that first. It's just periodic families. All right, so Monday we are demonstrating our understanding of periodic families, the differences between them and similarities. It looks like you're going to see it. So it's off. Sorry. We'll continue then with atomic size. Ava, I thank you so much for saying like, oh, it's like confusing. It is confusing. And that's the kind of thing that we need to think about on our own. And does it make sense in your mind? I hope you guys have a great weekend. Best of luck. Amazing football champions.